we were talking last time about functions, function notation, so domain, range, those kind of things. We're going to get into graphs of functions here a little bit. Today we're going to get into the idea of even, odd, periodic functions. Graphs, specifically talked about graphs a little bit today. We'll have a quiz on Thursday. Okay, our first quiz will be on Thursday, and it's going to be a lot of function notation, graphs, and not necessarily with a calculator. Like, for example, today's section 2 is on graphs, and they're almost all no calculator stuff. I mean, because quite honestly, I mean, a graph with a calculator is not a big deal. You just go in, you type it in, set a window, and there it is. There's your graph. So being able to do graphs, being able to know what the graph of certain functions look like without a calculator, that's a big thing that we've got to do in the next couple days as well. You know, that you know what a parabola, if you see an x squared, it's going to be a parabola, right? What's a sine graph look like? You know, what's an e to the x graph look like? You know, and if you shift and stretch and thing, you graphs, right? We're going to talk about that today too. Because we deal with a lot of functions in the no calculator stuff, we just need to know some of these, what they call elementary functions or basic functions, what those do. So we don't spend a lot of time on our calculators. I'm trying to think if we use our calculators on the quiz, on this first quiz. You know, sometimes many of our quizzes have a calculator part and a no calculator part. There will be some quizzes that might just be no calculator the whole thing, and there might be some quizzes where the whole thing's calculator. Now remember, just like on the AP test, just because it's a calculator part doesn't mean you need your calculator for everything on it, right? It's just you're allowed to use it if it's needed, right? But sometimes our problems are written in a way where the calculator really is no use to you anyway. So I think about this quiz, I think one of the things I told you last week, I want you to be able to graph a function on your calculator, be able to set a window, be able to trace, understand what it means in the context. So I think we will be using the calculators, and I may just give you the calculator for the whole thing, but it'll probably only really be helpful on a few things, is probably what will happen. You'll see as we go through the thing here. Okay, so number 12. Well, I anticipated this. All right, so number 12. Definitely want to be able to do number 12. This is something I told you last time on Friday that you will be doing this on the quiz. There will be something similar to this, very similar to the one we worked together in class, and you will write a piecewise function. So we need to know that the equation of a circle is this. Okay, so that would be something to put down in your notes to study by Thursday, that you know that, and then be able to get y by itself on that, and then also lines, slope, point slope form, you know, that we can work with that. Okay, so if we look at the two lines like this, now my graph, and I don't know if the book was a little bit this way. Maybe that might be some of your question. This is kind of a misprint typo. I'm not going to make you guess, you know, probably. I mean, it's supposed to hit right there, okay? Most of the other points look like they do. I think the book, is your book better than this, or does it look about like that?
It's the same as that.
It's just like that, okay. So that's kind of just a printing error there, so we're going to assume it's right there, okay? So this would be the line what? Y equals -2, right? Y equals -2. Now, we already got the y equals right here. So y equals -2 would just go there. Okay? And then that goes from where to where. Now, it doesn't, I would say for graphs, this would happen on the quiz. Anytime you see a boxed in, like a grid boxed in, we just assume it stops right. Now, if you had -infinity to there, I wouldn't count wrong necessarily. But I think what we should do is if it's boxed in like this, we're just going to assume it stops right there. It's inside that grid. If it's just an axis and there's arrows on the end, you know, then we can assume otherwise. But so this is going to go from -5 to -3. Okay. Then we got the half circle, which I'll skip that one for right now. And now let's go to this line. So this line would be y equals, what's its slope? Looks like it's down 2/1. So -2 slope. And then if we use this point right here, which is 2, 2, is that right? So x minus 2 plus 2, and you can just leave it just like that. Negative 2, x minus 2 plus 2. Is that right? Yeah, I think so. Right? And then that goes from 2 to 5 included. Okay, and now if we go with the half circle, so now if we do our work down here, so I would have, where's the center of that circle? It looks like it would be right here. So 0, negative 2, so x minus 0. Now that I can just definitely leave out that 0. And then y plus 2, quantity squared, and the radius is 1, 2, 3. Is that right? Good. Okay, so this would just be x squared, so I'm going to subtract that over. So y plus 2 squared equals 9 minus x squared. And then I'm going to square root that. Now remember, when you square root, you got plus or minus square root. But which one do we want? Positive, because we have the top half of the circle. Now we don't have the whole half of the circle, but we don't care about that, right? Because we'll take care of that in our domain. The circle will just go from negative 3 over here to 2. So, but we have the top half of the circle, so that's a positive square root. Now, also, and you don't have to admit it in front of everybody, but I'm guessing there's some of you sitting here thinking, oh, if I square root this, that'd be this. You don't have to admit it, but that's not true, right? That's not true. Because 9 minus x squared is not the same as 3 minus x, right? I mean, a simple little test. If I had 16 minus 4 and I square root that, that is not 4 minus 2, right? 4 minus 2 would be 2. 16 minus 4 is 12. Square root of 12 does not equal 2, right? So the square root of 16 minus 4 is not 4 minus 2. So the square root of 9 minus x squared is not 3 minus x, okay? So don't be tempted to do that. All right, and then we want the positive square root, and then we subtract 2. So that would be negative 2 plus square root 9 minus x squared, and then that is from negative 3 included to 2 excluded. There you go. Okay.
Would it be the top of the parentheses negative 3 because the other one was...
Thank you. Just testing you. Since I included the negative 3 there, I should not include the negative 3. Okay. Yes, sir.
Does it always matter which one you include?
Nope. So since this one goes to negative 3, and then this one also this one takes off from that same spot, right? But if you ever get this gap here, would it be okay to have that filled in? What's wrong with that? Right, but I mean, what if this would have been, would I even give you one like this? No, because it's not a function. It fails the vertical line test, right? So whenever you have that gap, that jump in there, you're going to have one open, one closed. But when they're connected, then you don't want to say it's kind of a technicality. It's not a huge deal. But yeah, I would probably, on the EP test, they would probably take off a point there. So it doesn't matter. This could be excluded and this one be included. Just make sure one of them's included, okay, and one of them's not. All right, so that's number 12. Be prepared, put a big star by that, whatever, in your notes for Thursday. Review that, okay? Be able to do that. All right, 19, was that the next one you asked about? Okay, so this is a little bit of foreshadowing for stuff we're going to do when we do areas later on. We've already done some area problems, with those exploration worksheets we did. This is a type of question you're going to see in Chapter 7 for sure, maybe Chapter 5. So they say that they're wanting you to create this function a of t. So they're wanting you to create the function a of t. And again, everything we do is about functions. And so, again, a function is something that accepts an input and has only one output for any of its inputs. So they said, here's the line L, 2x plus 1. Let a, the function a, be the area bounded by what? This line L. What else does it say? The x-axis and the y-axis. and the line x equals t. What's a line x equals look like? Vertical line, right? But where's t? Well, could be anywhere, right? Now, actually, it could be over here, but we're going to draw it over here because it makes it easier to look at for this problem. But we don't know where it is, so I'm just going to draw it right through here. I'm going to purposely not make it right on a nice point because I want you to understand it's not, doesn't have to be. That can move. Think of that blue line as being able to just slide around. Okay, and we'll keep it over here to the right of the y-axis, but just think of this blue line being able to slide around. Well, if you bound a region by the line L, the y-axis, the x-axis, and this line, maybe you can see it already. Isn't it going to be that right there? And what shape is that? Trapezoid, right? Just kind of like what we were talking about with trapezoids the other day. But there is an area, and understand why this is a function. Understand why a of t is a function. T is the input. So if I move t to a new spot, I get a new area. Move t to another spot, I get a different area, right? And how many areas would be corresponding with any one t value? Only one. That's why it's a function, right? You move t to a new spot, you get an area associated with that new spot. So t is your input to this function. So the position of this vertical line is your input, and the area that's generated is in your output. Okay, so that's a function. So yeah, the line L is a function also, but this is a function using t. Okay, so all we need is the area of that. Well, the area of a trapezoid is 1/2 b1 plus b2 times the height, right? So we got 1/2. So, I mean, again, this is one of them that I'm looking at when I go around and I see people on their paper and all they had was a of t equals t squared minus 1/2 t or whatever. I don't remember what it comes out to be, right? With no picture or anything, right? I mean, come on now. Try to draw, at least draw the line 2x plus 1, right? At least draw a graph, which many of you did, which was good to see. All right, what is b1? It's this side right here, right? And as t slides around, is that going to change? No, that's always going to be 1. Plus b2. What's b2? That's that. What's that going to be? Is that t? Because t right now is like 2.5, right? I mean, let's pretend t was 2.5. Let's pretend t was 2.5. How would you get this?
Oh, you plug it into that equation.
You plug it into the line equation. This is the output of the line equation. Here's the line equation, 2x plus 1. So if you plug a 2.5 in here, you're going to get 2 times 2.5 plus 1. Or if t's a 1.5, you're going to get 2 times 1.5 plus 1. But if t is just t, what do you get? 2t plus 1. We should have t's over here, right? We should have t's over here. It's a of t. It's a function in terms of t. So plug a t into this function, right? You get 2t plus 1. All right? And then what is h?
Just 2.5.
No, well, 2.5 was my example.
Oh.
This is h right here. What is that? T. T, right? If t's 2.5, this is 2.5. If t's 1.5, this is 1.5. If t's 1, it's 1. It's t, right? It's t. So the height is t. So there you go. So 1/2, 2 plus 2t times t. Take that times 1/2. That would be 1 plus t times t. And that would be t plus t squared. I guess it was minus it. And that would be a of t, right? So move t to 2.5, plug 2.5 into there, you get your area that you would be generating, right? There you go. Okay, stuff we're going to be doing later on. You're going to hear a lot of that. You'll get really good at that. Okay, find the area of the region bounded by this curve and this curve and this curve. You'll be able to get that. Okay, 22. We didn't ask about. It was 24. You said. Anybody want 22? Why did I have that down there? That's so strange. 24, somebody asked about, explain why the rules f of x equals x squared plus 3 over x and f of z equals z squared plus 3 over z are the same function. And maybe your question on that is just, how do you explain it? Well, because for any given input, they're going to have the same outputs, right? You plug 1 in for x into the first function, plug 1 in for z into the second one, you're going to get the same output, right? And so I usually kind of have this little thing I'll talk about. You'll see me bring it from time to time. But f of x is equal to x squared, so f of a would equal a squared, and f of 2 would equal 2 squared. Now that's a specific function. And f of German shorthair, that's a German shorthair, would equal German shorthair, right? I mean, there's nothing magical about x, right? That's why I talk about inputs and outputs. Okay, there's nothing magical about x. Most of our functions we use x, but it could be z, it could be u, it could be t. T a lot of times, because a lot of examples we use, especially differential equations, use time as the input, so t is used in a lot of functions that we deal with. Okay. I guess the question I had on 22 was part C. Did we talk about that? Okay. Absolute value function, right? The absolute value function, most people just say, oh, it's a V graph, right? It's a V graph. We know the absolute value function, easy. Okay? Absolute value function. But we're talking about absolute value, as a matter of fact, in my Algebra 1B class right now. Okay? So let's go through it. Domain, what's the domain of the absolute value function? The absolute value function is, we'd be saying, what is it legal to plug into here? All reals, right? All reals, I'm fine with that. Negative infinity to infinity, right? That'd all be good. What's the range? Y is greater than or equal to 0. I'll take y. I don't think y was given to you anywhere in there. You could say, this, but I understand y typically means outputs, okay? Or you just put 0 to infinity. That'd be a good way to do it too, right? Any of those, okay? And then is a piecewise function, okay? So if we call it f of x, okay? Well, there's two pieces, right? I mean, think about the one we just did. This is just a way easier version of this one, because this one only has 2 lines in it. So it's got 2 pieces. What's this first piece? That'd be y equals what? Negative x. And that would go from negative infinity to 0. If we want to include 0, include 0. And then what's this one? Y equals x. And that's from, since I already included that, most of the time I think we would probably include the 0 here probably and not here, just because, it's just easier. But the idea is, isn't that what absolute value is? If it's positive, you get out the same thing you put in. So you put in an x, you get out an x, if it's positive. If it's negative, you get out the opposite, right? If you put in a negative into absolute value, you get out the opposite of x. So that's really what it is. But really, now that we've been talking about piecewise, if you just graph it, you say, okay, what's this piece, what's this piece? So, okay? But that is the absolute value function by definition. By definition, that's what it is. Okay, the bars just are something we made up to, kind of tell us about the absolute value function, but that's what it is. Okay? All right, 28.
Actually, I realized I did part of it like the wrong section, because that's why I was so confused. Because in school I did the right one, and then when I switched to the wrong page, I did the wrong part of the next section.
It couldn't have been. It wasn't probably too awful bad, but
yeah.
Yeah, but yeah, that. Something else. All right, 28. What are we doing here? Oh, this is the reverse here. We're supposed to sketch the graph of this particular thing. Okay, so on 28, so it's y equals, the key is, I think, on the piecewise, remember, f of x equals y equals, so it's y equals 0. Okay, if x is less than or equal to negative 1, so that's just here. That's just that horizontal line right there. Y equals 0, less than or equal to negative 1. Between 1 and 1.5, we have this line. What I typically do, especially if you're using pencil, so you got 3x minus 2, is I'm going to graph these things and erase. Okay, so 3x minus 2 is going to be down here, and then it's going to go up 3 over 1, and it's going to go up 3 over 1, right? And so I'm going to get this line right here, except I only want it between 1, and I don't want to include the 1, and I don't want to include the 1.5, so I'm going to come in here and I'm just going to erase. And let's see, what's 1.5? That'd be 2.5. So that goes to about right there, right? And then just erase the rest of it. And so I don't want either parts of that, so that's actually an open circle. Open circle, 1.5, 2, right? Or excuse me, at 1 and at 2.5. Okay, and then from 1, and then I want x squared. Okay, so then again, I would come in here, now this gets a little bit strange. Let me erase that. Now x squared is going to go through here, and then it's going to go through 1, 1, and then it's going to go through 2, 4. But it's going to be curving below this. So it'll come through here like so, but I don't want that part. And then it's going to be curving kind of below it and skip by it there and then come up and go through the 0.24. It's kind of hard in a small way to make this work. And so x squared, so if you take 1.5 squared, that's 2 1/4. So right here, right below that would be kind of that point. So I'll erase this other part. So I don't want that part there. And then it goes to where? To 2. So I don't want that. And it doesn't include the 2, so that's open. So at 2, 4 we have open and it kind of curves, but it's right below it, right? There's a little bit overlap. Okay, that's not real great, but here, if I can get real picky there, but. So there you go, be able to graph it. Now, domain, what's a domain? So when you're looking at a graph, I think looking at a graph is the easiest way to do domain and range, right? So domain's all the possible x values. Well, that goes all the way from -infinity to -1, including -1, and then I just put a comma. And then where? From 1. Yeah, you could break it up. You could go 1 to 1.5 excluded, and then go 1.5 to 2, but why not just go 1 to 2? Isn't that true? Aren't those the x values? I mean, but you could go 1 to 1.5 excluded, both of them, and then go 1.5 included to 2 excluded. That'd be fine. But 1 to 2 would be the same thing, right? And then the range. Basically, the domain is the right side of that piecewise function, right? I mean, this is your domain right here, right? Which, of course, would be -infinity to infinity is how we wrote it. But you could just write that to be the same thing. Here is the domain on this problem, from here to here to here. Now, it turns out that's the same as -5 to 5, right? On that one, we could just say -5 to 5. It would be the same thing. So either way, I'd be okay. But all right, and what's the range here? Range is all the possible y values. Well, you got 0 here, so you can just put that by itself. Sometimes you'll see it in curly brackets or something, but you could just put a 0. I don't care. I'm not going to get picky on that notation. And then the y's go from where to where. They show a picture in your book of like if you were shining a light here or this direction, you were shining a light, and the shadow on the y-axis would be the range. I thought that was an interesting way to say it. So if you shined a light here, the light would go through here. There'd be a shadow on the y-axis through here. I thought, well, that's kind of interesting. But the y's go what? From 1 up to 4, and it hits them all, except it doesn't include the 1. It doesn't include the 4, but it would hit all of them in between because there's this overlap here. Sometimes you get gaps, and so then you have to separate it. So something like that. You could just do this too. That'd be fine with that. Okay. All right. Domain range. And then what did you say? 30? Did somebody ask about 30? 4 minus x squared. Okay, so when you get something like this, you got to ask yourself, what are the possible x values? Well, is there anything that would be illegal to put into here? Well, what are the things that are illegal? Typically dividing by 0 and negatives inside of a square root, right? Because if you put a negative if you get a negative in a square root, you don't get an output. And so it's not in the domain. If you can't plug it in and get an output, then it's not in the domain. Okay? Well, there would be some problems here, wouldn't there? Anything bigger than, well, if this was bigger than 4.
Oh, but like 2.
So that means if x is bigger than 2 or littler than -2, right? Like -3 squared would be 9. 4 minus 9 is -5. So it looks like you're going to have to be between -2 and 2, right?
Isn't only the natural domain? So like, wouldn't that only be natural numbers?
No. That's what natural domain is. Okay, so let's talk about this way. So I may give you a problem where I'll say y equals x squared, and I only want you to look at it from 1 to 4. Okay, so for that problem, the domain is 1 to 4. The natural domain is just what is the, if you don't restrict it at all, what is the domain where, what are the allowable x values where you get a y value? Okay, so that's what they mean by natural domain. Okay, so natural domain is -2 to 2. Okay, anything outside of that, you're going to get negative in a square root, which is an imaginary number. It's not going to be a member of the reals. There'll be no alpha. Okay, what about the range? Did they ask for the range? Let's just talk about what would be the range. They didn't ask for it, but what would be the range? 0 to 2. Because the biggest, so this is always going to be positive, right? So the biggest this is going to be inside here is 4, right? Because you're going to have 4 minus a positive number, 4 up to 4. So you're going to get numbers between 0 and 4. And so it's going to go 0. So you could get 0, and you could get, what did we say? 2, right? That's the biggest you can get there. Okay. Well, it turns out what this is. Okay. What this is a half circle. It would be good, it will be good later on that we recognize this, because think about it. If you square both sides, you get y squared equals 4 minus x squared, and then you add the x squared over, you get x squared plus y squared equals 4. Isn't that a circle at the origin with a radius of 2, and it's only the top half of the circle, right? So if you look at this, that's going to be your function right there. Oh yeah, it's going to go from -2 to 2, and the range is going to be from 0 to 2. Okay, so it makes sense that that's what we got. So, and that's why I say I think graphs are easier to get the domain of range. So if you would have recognized this as a half circle, then all of a sudden the domain of range becomes really easy. All right, so let's move ahead then into section 2. Let's just keep running going here. So if you turn to page 11 in your book, over into page 12, just a lot of terminology here. If you go through the book here, you see a lot of bold-faced words. Most of them are going to be very familiar to you. So, you know, we'll go through this pretty quickly. We've already talked about the vertical line test for a function. Function notation. So we spend a lot of time in this class. You know, when we talk about a point, like they label it here, a f of a. We'll often do that, right? A f of a. So we're using the input value. When we talked about the slope formula, you know, back in algebra class, you talked about slope this way. Okay, we're going to think of slope between 2 points this way. Okay, it's the same thing, right? It's the same thing. But it's just using your a and your inputs, and then those are your y values right there. F of b is a y value. F of a is a y value. Whenever you hear f of 2 or f of a or f of b, you think y value. Okay. So just some notation to get used to. Down at the bottom, it talks about continuous functions. When we get into chapter 4, we're going to talk a lot more specifically about continuous functions. But continuous functions mean no breaks. Now, we've already looked at some examples. That is not a continuous function. Okay, it's got several breaks in it. It's got a break here. It's got a break right there, kind of a gap. Okay, continuous function is basically, you know, you can just smoothly draw it, never lift your pencil, basically, that kind of thing, right? This is a continuous function, right? Even though it's 2 pieces, we drew it as a piecewise, it's still a continuous function. So a piecewise function can be continuous, okay? This was not continuous right here. Now, if this line would have taken off from here and maybe went that way, that could have been continuous. But there's that gap in there, okay, where we'd have to lift our pencil. So that's what it means to be a continuous function. If we turn over to page 13, talks about X and Y intercepts. We've dealt with those before. Increasing, decreasing, of course, that seems pretty basic when a graph is increasing or decreasing. Turn to page 14. Here's some new terms for us. First of all, a root. A root is where it crosses the x-axis. That's also called a zero of a function. It's called the root of the equation. It's called the zero of the function, but they're pretty interchangeable. The zeros, it's where it crosses. Those are the x-intercepts. Okay, roots we're interested in. It's when the y is 0. Some special points. These are some terms that are going to become really useful for us that we'll use a lot. Local maximum and local minimum. So this would be a local minimum right here. This would be a local maximum. Now we're going to distinguish those. I'm not sure they talked about those here, but we're going to have what's called a global maximum and a global minimum. Let me show you the difference. Okay, so if I go like this, okay, this is a local minimum, but this is the global minimum. That is the lowest point. But local maximum are more like peaks and valleys. Now they can be, this would be a local maximum, but it's also the global maximum. It's the highest point, but it's a local min or max. Now, sine curve has a bunch of local mins and maxes, right? I mean, everywhere along there. And they're all global maxes, but usually when we talk about global max, we talk about the y value. So on the sine graph, the global max is 1. It just hits at a bunch of different places. But this would be a local max point. This would be another local max point. This would be another. So a lot of times with local max min, we talk about the x value. Where is it? With global max min, we talk about what is it, because we want to know what's the highest y value, what's the lowest y value. Okay? But sometimes we want to know where it is. Where is the local max min? So we talk about where its x value is. So that's local max, local min. Think about peaks and valleys. You can have a sharp point. That's what we'll call that. That's a sharp point. Now, something special in calculus happens if you get a graph that has a sharp point that's not nice and smooth like this, okay? We'll get to that later. But that would also be a local minimum right there. That's a local minimum. Okay, local means kind of in that small area, that's the smallest, that's the lowest point. Okay, local max min. All right, also we'll talk about concave up and concave down. Okay, so like if you look at this S graph right here, okay, this is what we call concave down. On the I graph here, right through here, that's concave down. Okay, concave up is in the reverse of that. So this graph, somewhere in here, this graph switches. I don't know, maybe right in here somewhere. This graph switches from concave down to concave up. That's called an inflection point. An inflection point. You see that in the middle of page 14. Switching from concave down to concave up. Same thing with this one. This graph starts concave up. You can see how it's kind of curved upward, and then somewhere, like right around in here somewhere, that thing switches to becoming concave down. And then it switches again, looks like over in here somewhere, it switches again from concave down, and then it's concave up. Okay? So some people say like holds water and versus doesn't hold water. Again, this is concave up here, and then it looks like in here somewhere it switches to concave down. So anything that's curving has to be one of those two. It has to be concave down or concave up. Okay? And we're going to learn some more stuff about that. All right. Then on 15, we talked about tables of data. So remember, if I give you a function that's just a table of data, that's all we know. If that's all we define it as is that table, then all we know are those points. So if you look at that bottom left graph on page 15, that would be the graph of that function. Who knows what happens in between, right? There is no right graph there. If all we have is a table, we don't know. All we can say for sure is it's those distinct points. Okay? Turn over to page 16. Okay, so let's talk about translations. That's probably the main thing we have to talk about today, I think, and then also the odd even stuff. The rest of this was pretty basic as far as just some terminology. So let's talk about shifting and so forth on graphs. Now, you did this a lot with the sine graph, right? You did a lot with the sine graph, phase shift and shifting them left and right, shifting them up and down, and then compressing them like the period change. right? The period would change, so you'd stretch and compress, and amplitude, remember amplitude, you know, you'd stretch this way. But it doesn't just apply to the sine graph, it applies to any graph. So I'm going to use the example of x squared. All right, so can somebody tell me what this x minus 2 here does to this graph?
Shifts it to the right too.
He says right. Agree? Shifts it to the right. Now that seems strange. It's subtract. To me, that negative, that seems like left. Why is it right? Now sometimes that is confusing to people. Again, from last year, you did so many of them, maybe it's not that confusing. So I want to try to just show you real quickly why it is. Matter of fact, what I will summarize from this is whenever you act on the inside here, except for reflecting, that would be different. But when you act on the inside, if you compress or stretch or you shift on the inside horizontally with the x, it's always the opposite of what you would think it would be. Okay, and here's just a simple example why. So if I took the f graph here, this is x squared, and I did f of 2, which would be 4, okay, that's this point right here. On this graph, since we know it's a horizontal shift, we all agree with that, right? And again, the way I remember that is when it's on the inside, when it's on the inside of the function, it's inside of the squaring, that tells me it acts on the x-axis, so that's going to be a horizontal action, okay? That means this is going to move this way. Well, where does this point move? Well, it's got to stay up here at 4, so it still has to have an output of 4. So what g would I need to get an output of 4 here? What would I have to plug in for x to get an output of 4? 4, right? So if I put in a 4, well, also a 0, but that would be because of this one, okay? So I could put in a 4, or I could put in a 0, and I would get an output of 4. I should have done those in red. All right. So g of 4 is 4. So that means I'm going to have a point here. That means that g graph's going to have a point here and here. Well, we can see what happened. That one just shifted there, and that one shifted there. Okay, so it makes sense. So it did. I see why it happened. It did work that way. It was a shift to the right, even though it seemed like it should have been a shift to the left. Now, what happens if I put that minus 2 on the outside, like that, outside of the squaring? That's going to go down. Now, that time, it did what we thought. It's a subtract, and it went down. So that's weird. Here it was a subtract. You'd think it'd go left. It actually goes right. But when it's on the outside, it does what we think it would do. And again, simple way to tell that, let's say f of 0 is 0. We think this is going to go down 2. So that means we're going to have the same we're going to have the same input this time. We're going to have the same input this time, but this time when we put in a 0, we get what? Negative 2, sure enough. So 0 on the red graph, it's going to be there. That point is going to go down 2. Makes sense. Okay, so now let's talk about this. I didn't have time this morning to write up this. So we got our regular parabola. What happens if I put a 2 on the outside? That's that amplitude thing, right? But what it really is a vertical stretch. So it's going to take all of the points, and I like to think of it stretching both ways, right? It stretches both ways. Anything below the x-axis is going to go down, and anything above is going to go up, okay? Now, all of this is above the x-axis, so it's all going to stretch up. But what's going to happen here? So that means that if we have, let's just do, now we better do 1, otherwise when we stretch, that's not going to be good. So f of 1 is 1. We think it's going to take that point and stretch it to there. So in other words, we're still going to plug in a 1. We're still going to plug in a 1, and sure enough, 1 squared is 1 times 2. There you go. That point is actually going to stretch to there. What's going to happen with... But it's not a shift, because f of 2 we know is 4. What's g of 2? 2 squared is 4 times 2 is 8. Okay, so this one goes way up to here. Okay, and so it's not just a shift. That one, this first one only went up 1. This one goes up 4, so it's definitely a stretch. Okay, so that makes sense. And number like 2, what if that was 1/2? Then these points would have they would have squished down here, and this point would have squished down to here, and it would have been compressed. It would have been compressed. Okay, so you get a number less than 1 on the outside. It's going to compress vertically. If it's a number bigger than 1, it's going to stretch vertically. But last situation then, if we take, and this is the one that is sometimes tricky, if we take our regular f of x squared, and we put a 2 on the inside. What does that do?
Just a stretch.
Let's try a couple of points. All right, here's a couple of points here. Now what we think it's going to do is work in which direction? Horizontal or vertical? Should be horizontal. Why? Because it's on the inside. Again, anything on the inside of the function, it's inside of the squaring action. Anything that's inside the function is going to act on the x. It's going to act horizontal. It's going to act on the input. Anything outside of the squaring action, anything outside of the function is going to work vertically on the y, on the output. It's on the outside. Okay, so that's the first thing we've got to make sure we remember. So this is going to act horizontally. So what's going to change is our inputs, right? So these points are going to somehow move horizontally. So, okay, their y value is going to stay the same then. So that means g of something's got to be 1, and g of something else has got to be a 4. Okay, well, look at this. What would it take for this to have an output of 1? What does x have to be? Doesn't x have to be a 1/2? Because you're going to take 1/2 times 2, which is 1, and then square it, and that gives you 1. How could this be a 4? If x is what? If x is 1. So what did it do to those inputs? Compressed them, right? In other words, this point here, f of 1 is 1. In the new graph, that point's right there. This point here, f of 2 is 4. That point is now right there. G of 1 is 4 on this graph. So this graph is compressed. And so then, of course, there would be these mirror points over here. Right? So, again, like we were saying with the minus, when you have -2, that feels like it ought to go left, but it actually goes right. So anytime you have a number on the inside, it acts the opposite of what you think it'd do. So you see a 2 on the inside, you think it should stretch it 2. No. It compresses by a 2 factor, okay? And that shows it right there, okay? It compresses it by a factor of 2. So if this was at an x of 1, it's now at 1/2. And it compresses in both ways, okay? So what kind of number on the inside would it take to stretch it? It would have to be a number less than 1, right? Think about that. So what would give me an output of 1 on that one? An input of 2, right? I should use different color here. Let's use black for this. Okay? So G of 2 would be a 1. So instead of f of 1 is a 1 here, it would be G of 2 would be a 1. Okay? So it would actually take that point and stretch it out by a 2 factor. So this point that was at 1 is now there. Okay. All right. So, yes.
Wouldn't it be a vertical stretch to the red one because you're like it's still like amplifying the y coordinate?
Okay. Okay. Right. So when you look at that, okay, so we just talked about why that's a horizontal compression, right? But then you look at the result and you're like, oh, it's just a skinnier parabola. Isn't that the same thing that would happen if you would vertically stretch it? Okay, yes it would, but it's easy to see why, because look at the way I wrote it. I wrote g of x was equal to 2x squared, right, where the 2's on the inside, but simplify that. What's 2x squared, 2x quantity squared equal to? 4x squared. Now what does that become? That's a vertical stretch of 4, right? That's a vertical stretch of 4. Well, sure enough, this point that was down here at 1, 1 is now up here at 1, 4. Right? So on a parabola, that's not true with all graphs, but on a parabola, a compression of 2 horizontally is equivalent to a vertical stretch of 4. They're the same. Right, yes, absolutely. And you know what's interesting that most people don't think about is that you never talk about this in algebra because it's like we don't want to complicate things. But here's your basic y equals x graph right here. What is y equals 2x? Change color. What's y equals 2x? In the language of what we've just been talking about? It's a vertical stretch of 2. And so sure enough, this graph gets steep. By the fact that it's a vertical stretch. What's this graph right here? It's a downshift of 4. Now, actually, because y equals x is x to the first, you could actually think of that as not only a downshift of 4, you could think of it as a, what other kind of shift? A right shift of 4. It's the inside and the outside are kind of the same thing for a linear. It's a simplistic example. But you think about it, y equals x minus 4. Oh, yeah, that's just a y-intercept of this with a slope of 1. Well, if you look at what that is, it's just a downshift of the black graph, or you could look at it as a right shift too, right? So line, so slope and y-intercept and that kind of stuff is the same thing. It's the same thing. It's stretching, compressing, shifting. Okay, same exact scenario. Okay, so here's what you're going to have on some homework. You're going to have a situation where they're going to say, okay, this is a G graph here, and you're going to graph, say, G of 2x. Let's just do one that we kind of struggled with there. So you're going to do G of 2x, okay? So you're going to draw a graph. So when you get to that section, you're going to have about 6 different or 8, I don't know how many you're doing, of these pictures on your paper. So I'm going to be looking for that when I come around tomorrow and look at it. So what does that mean? What does G of 2x mean? What did we just say? Which way does it go, horizontal or vertical? It's on the inside. It's with the input. It's with the x. It's on the x direction. It's horizontal. What's it going to do? It acts the opposite of what we think. It's going to compress by a 2 factor. What does that mean? That means any x value that is here at 1 is now going to be where? At 1/2. So this point that is here at 1 is now going to be there. Okay, I'm going to cheat. I'm going to actually do mine on here. Okay, so that point is going to be, and that's not a bad idea either. If you want to draw this graph 8 times and then do the one, so this point is going to move into here. What about this point right here on the y-axis? It's the same, right? Because we compress towards the y-axis. Okay, this point that's out here at 2 is going to be in at 1. I'm just going to do all the corners. If I do all the corners, kind of important points, how about this root? It's here at -4. That's going to be in at -2. This one that's out here at -5 is going to be in at 2.5. This one out here that's at 5 is going to be in at 2.5. This point that's here at 2 is going to be at 1. And there it is. So there is my compression by a factor of 2. Okay? All right. So that's the kind of, oh, the ones I forgot. What about a negative? What about a negative on the outside? So if you have G of x, what about a negative on the outside? Vertical flip. Flips over the x-axis, right? But it's vertical. It's on the outside, so it acts vertically. So it's going to be a vertical flip, okay? And if you've got one on the inside, that's going to be a horizontal flip, okay? Everything that's over in this side of the y-axis is going to flip over here. Everything here is Okay? So, horizontal vertical reflections or flips, horizontal vertical shifts, horizontal vertical stretch and compress. All right, that's it for those. Okay, that's all I got on that, but I guess we do have to turn to page 18, 19. Let me just talk about even, odd. So let's just write this down real quick. So an even function, there's several things to say about an even function. Let me give you two quick examples, and then you'll be able to tell me about it probably. There's one, and here's another one, cosine prime. Okay? What is it that makes those even functions? What do they have in common? What kind of symmetry? Y-axis symmetry. So y-axis symmetry is an even function. So we get an exact copy on the left side of the y-axis and the right side of the y-axis, okay? It gets its name from the fact that, like, for example, x squared has an even power. That's an even function. Now, not every x squared is going to be an even function. If I take x squared and I shift it 2 to the right, it doesn't have y-axis symmetry anymore, right? So just because it's an x squared doesn't make it an even function, right? So they might ask you, what y equals x squared plus 5x? Is that even, odd, or neither? Well, it's going to be neither, right? Because that one is actually moved off of that y-axis symmetry, so it would end up being neither. So just because it's an even power doesn't make it an even function, okay? Y-axis symmetry, here's how we, here's the more mathematical way to write it, and that is that remember f of x means outputs? F of x means outputs, so that means when you put in opposite x's, opposite inputs, you get out equal outputs, okay? So, for example, you put in 2 and get 4, put in -2 and get 4. You get the equal outputs. That's the symmetry. So, opposites in, a lot of times we say opposites in, opposites out. Excuse me, not opposites out, same out. Opposites in, same out. Okay, opposite inputs, same outputs. Okay, that's an even function. Odd function. Give you a couple quick examples. X cubed, and the sine function are two examples of odd functions. What kind of symmetry is that? It's called origin symmetry. It's called origin symmetry. Okay? Now, this means opposites in, opposites out. Think about x cubed. Put in a 2, you get 8. Put in a -2, you get -8. Okay? Opposites in, opposites out. So you put something in, whatever you get out, if you put the opposite in, you'll get the opposite of that. Now, it wouldn't have to be, 2 and 8 are both positive, -2, negative are both positive, or both negative, but it just put opposites in, you get opposites out, and that looks like this. F of -x is equal to negative f of x. So notice you got opposites in, one has x in, one has negative x in, and then there you get opposites out. One side you get f, one you get negative f. Okay? Opposites in, opposites out. That's it. Okay? Now, a quick test. So how would I ask you this in homework or on the quiz? If you've got your calculator and you can graph it, you can talk about symmetry. You can say, yes, it is. It has origin symmetry. Yes, it is an even function, has y-axis symmetry. If you had to show it without a calculator, you had to prove it with an equation, it looks like this. So is, let's say, x squared minus 4, is that an even function, right? Well, one way to show that is put in an opposite x. And so you put in opposite x squared minus 4, and sure enough, what's opposite x squared? X squared minus 4. So you get, okay, you get the same thing out. Opposites in, same out. So that shows that it is even. So that, whoops, that's one way to do it. It's really not good enough to just say, hey, you put a 2 in, you get 0. You put a -2 in here, you get 0. What worked out one time would have worked for all numbers, though, right? So it really doesn't work to just try one number and see that you get the same out. And what about an odd function? Is this an odd function? If we had x cubed, let's see. What would be an odd function? Well, if I shift that, that doesn't work very good. Yeah, we won't. But see, that goes back to your coterminal angles and all that stuff in trig kind of makes sense too, because if you do sine of pi halves, what's sine of pi halves? What's sine of pi halves? Here's a unit circle. Sine's the y, 1, right? What's sine of negative pi halves? Well, negative pi halves is down here. Oh, look at that. Negative 1. Opposites in, opposites out. Right? Sine's an odd function. Cosine, on the other hand, what's cosine of pi 6? Oh, good. Pi 6 right there. Cosine, square root of 3 over 2. What's cosine of negative pi 6? That would be right down here. Oh, they have the same x. Remember, cosine's the x, sine's the y. These 2 points down here have the same x-coordinate. They have opposite y-coordinates, but they have the same x-coordinate. But since you know cosine is an even function, you don't even think about it. You get cosine of negative pi 6, you say, hey, it's an even function. All I got to do is cosine of pi 6. I'll get that because it'll be the same. They're even functions. So opposites in, opposites out. So that can come in handy at various times, knowing that they're even and odd. Okay, last thing. Periodic function. If I ask you for a definition of a periodic function like sine and cosine, what would you say in 1 or 2 or 3 words? What is it that makes a function periodic? It repeats. Everybody always says that, and that's fine to understand that, but we got to understand what the word repeats means. Okay, if I gave you this graph here, right, would you say that's periodic? Would you say that repeats? I mean, the word repeats can be kind of iffy. Is it repeat? If those were exactly the same size humps and stuff, somebody might say, yes, that repeats, but that's not periodic. What does it have to repeat? It has to repeat the exact same y value. So that's why it has to be like the sine graph, where it gives the same y values over and over again. Okay, so it looks like this. Here's the formal definition of that. And that's why we say it gives equal y values. Remember, f of x is the y value. F is the y value. So f of x plus p, so that can be plus or minus p. P's the period. So that means you shift it left or right that many units, you always get the same value out. So with sine, it's like 2 pi. So if I go 2 pi units, I keep going 2 pi to the left or to the right, I always get the same y value out. Okay, so it's pretty easy to see if you graph one. You can trace and you can see. So if you graph one and I say is it periodic, you say yes, it repeats all of its y values. Make sure you don't just say it repeats, but it repeats the y values and give maybe the period. But there's some other ways to ask it that make you think a little bit. So what if I just gave you this? This is where a calculator would not come in handy. So let's say we said f of x was periodic. Okay, so I just told you f of x is periodic, and I told you that the period was 6. Okay, I just told you that we have a periodic function and the period is 6. And then I tell you that f of 1 is 4, and I tell you that f of 5 is negative 2. Okay, that's all you know about this function. So you can't graph it, there's nothing to plug into, there's no equation, there's nothing. Okay, and so what if I ask you for f of 19? What would you say? That's 4. How do you know? It's 3 periods away from this point right here. Right? So at 1, you're going to get a 4. And at 7, you're going to get a 4. And at 13, you're going to get a 4. And at 19, you're going to get a 4. I don't know about in between, but every 6 units, I'm going to get a 4. Right? And so what's another one you know? What's f of negative 1? Negative 2. Because at 5, I get a 2. And at 11, I'm going to get a 2. And also going the other way. At 5, I get a 2. If I go back this way, 6, that'd be at negative 1, I'm going to get a 2. And at negative 7, I'm going to get a negative 2. And at negative 13, I'm going to get a negative 2, right? Okay, so if I know some values, I know every 6 or whatever the period is, I'm going to get those values again. And that's kind of what this is saying right here. Okay, so I think they give you some questions like that in the homework. All right, so 1.2 homework questions for tomorrow.